My lecture this morning was a little confusing, so I'll begin with some review. Was it confusing?
They're so confused that they can't answer.
If they don't answer, that means they're confused. So if I have a tensor, I could think of this as a linear map. And we saw that the tensor rank of T is at least the regular rank of this linear map. And I didn't say it, but needless to say, we could exchange the roles of the three vector spaces. And this is our classical lower bound. And so from now on, we assume that TA, TB, and TC are injective. And this is called concise. That is, our tensor could not be put in some smaller space. And the question is, say dimension of A, dimension of B, and dimension of C are all equal. When can we conclude that the border rank of T is the minimum possible? So I should make a remark explicit that I said implicitly. We can recover T up to equivalence from the image T of A star sitting inside B tensor C, this subspace, as, let say, x1 up to xm be a basis of T of A star. In fact, let's do it more generally. For any dimensions, then let A have basis A1 up to AA, then the tensor A1 tensor x1 plus A sub A tensor x of A is equivalent to T. That is, if we change basis, we get exactly the tensor T back. So this subspace contains all the information of our tensor. In particular, T is generic in any sense you like, if and only if this subspace is a generic subspace. So we can study the pathologies of our tensor T. In particular, we can study when it has low border rank by studying some corresponding pathologies on this side. And the main perspective of this lecture will be to work on this side over here. Now, we also saw that if we want to go back to exploiting the world of classical linear algebra, it's better to deal with maps from a vector space to itself rather than maps from one vector space to another. And we can do that as follows. So, well, actually, before that, let me make one more remark. So let's say T is concise, and the rank of T is exactly M. This is true if and only if there exist spaces, say AJ, BJ, CJ, such that T is some A1 tensor B1 tensor C1 plus dot 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 plus AM tensor BM tensor CM. If and only if there exist bases of B and C such that T of A star is equal to the space of diagonal matrices. So here, let me, here we're going to assume now that all dimensions are M, the same. And this morning, we discussed that given alpha in A star of full rank, that this T of A star, T of alpha inverse, which is now a linear subspace of the space of endomorphisms of B, is simultaneously diagonalizable. I.e., there exists a change of basis that makes this space the diagonal matrices. But here, when I say diagonalizable, I mean by conjugation. Here, to be diagonal, I get, so here, via GLB acting by conjugation, whereas here, this is really the GLB cross GLC. So the group is bigger, but we haven't pinned down an element. Here, if we pin down an element, we act by conjugation. And this point of view turns out to be preferable because there's a long history in linear algebra of studying such spaces. Now, we saw a necessary condition is that this T of A star T of alpha inverse, I'm not going to use the notation I used this morning. I'll just write it once, E alpha T. But I decided this is not necessary. That this space of endomorphisms is abelian. That is, all the elements in that space commute with each other. Now, the property of being abelian is that commutators vanish. And these are polynomials. So this is a Zariski closed condition. So that says that in fact for the border rank of T to be the smallest possible, that this subspace is abelian. And then we began to study when is this condition, is the condition of being abelian sufficient to conclude border rank of T equals M. So this is hopefully a review of the last lecture, and now hopefully the last lecture is less confusing. You have a question? If you even think you might have a question, if you ask, then maybe the students will be less shy about asking. Just a suggestion. No questions.
We start with the length of the T, but the conclusion is about the border length.
Right, because we started talking about if and only if conditions. And then we have just a one direction.
To be the border length.
Well, it started out as a if it's a minimal border rank, then this is an abelian subspace. But it's not true in the other direction. For example, it could have border rank M, but not rank M. So these conditions here, all of these conditions are not Zariski closed conditions. But this implication of these equivalent conditions is Zariski closed, and therefore it actually says something about border rank. Thanks. Other questions? Okay. So now I will go back to the proposition I stated this morning and prove it. Namely, we'll start to see that this condition may not be sufficient. So, yeah, so this condition here that there's alpha, so this alpha in A star with T of alpha full rank. Remember, I was calling this condition 1A generic. I will still use that terminology. So proposition T A tensor B tensor C, which is now Cm tensor Cm tensor Cm. One generic, concise, border rank of T equals the minimum possible M. Then this subspace T of A star, T of alpha inverse, where alpha is full rank, is closed under composition. So here's the proof. So being closed under composition is stronger than being abelian. So if I have any subspace, U contained the space of endomorphisms of some vector space. If this is diagonalizable, then U of dimension M then U is closed well, then first of all, U is equivalent to the diagonal matrices, and therefore U is closed under composition, because if I multiply two diagonal matrices, it's still a diagonal matrix. But now, being closed under composition is a Zariski closed condition. That is, it's defined by being polynomials. So being closed under composition, what does that mean? That says for all U prime in U, and say U1, UM, a basis of U, that the product UU prime is contained in the span of U1, UM. And remember, so this sits inside end of Cm, which is Cm squared. So if we take the wedge product in Cm squared, we get something that's 0. So this is a polynomial in these entries, and we're asking that that polynomial is 0. So therefore, this property extends to the Zariski closure of the set of diagonalizable matrices and that's what we wanted to show, that this the Zariski closed set, the Zariski closure of the set of diagonal matrices, this is exactly the images T A star T alpha inverse with border rank of T equal to M and the other hypotheses. So we have these inclusions. So this is among concise 1A generic tensors. We have the inclusion, so this is the same thing as the Zariski closure. Of the diagonalizable. This is contained in the
Maybe you can remind everybody what 1A generic means.
Yes, 1A generic is on this board. It's that there exists an alpha and A star where T of alpha is of full rank. You cannot see that, though, where you're sitting. And this is T such that T of A star, T of alpha inverse is closed under composition. So maybe I'll call this end closed. And this set here is contained in T such that T of A star, T of alpha inverse is abelian subspace inside NV. So it's a classical result from linear algebra that when m equals 3, diagonalizable is the same as abelian, so all three agree. When m equals 4, the same is true, but this is more recent. This is due to Ilyev and Manivel. And m equals 5, we had this tensor I wrote down where the image as a space of endomorphisms looked like this. And all the other entries are 0. And this space is not closed under composition. But is abelian. So in particular, the border rank of this tensor is strictly greater than 5. There's a kind of amusing story about this tensor. When I was working with Mateusz, we actually wrote down this tensor when we were preparing our paper because we were trying to find examples. And then it was pointed out to us that just a few weeks earlier on the archive, in completely different language, because it was the language of linear algebra, the mathematician Leitner, as part of her PhD thesis, actually put this example in that language in her paper, and it was also a counterexample to the property that, well, the same property, but she was studying it in a different language for the linear algebra question. She was studying the Zariski closure of the diagonalizable matrices as a subset of the variety of abelian subspaces. So sometimes people are thinking the same things at the same time, even if it's different language.
Could you explain again about this inclusion?
Yes?
Classical linear algebra or this last inclusion?
Yeah. So, so if I have diagonalizable matrices under some choice of basis, they will be diagonal. In particular, they'll be closed under endomorphisms. If I have a space that's closed under composition, and abelian, so this is and abelian. Sorry. Probably that's automatic. Let me think about that. But certainly if I add it, there's no harm.
Okay.
And then this is clearly a subset of being abelian. But I think because it's m-dimensional, that's abelian is automatic. But let me not say too many false things today. So now we have another condition, and we're very lucky because that condition is given in polynomials that we can actually compute. It's not so difficult to calculate if a space is closed under endomorphisms. So now we ask question, is being closed under, let's just call this end closed. Yeah. Is being end closed enough? Is, let's write it more carefully, T of A star, T of alpha inverse in B being end closed enough to conclude that the border rank of T is equal to M. So we found a further condition. We ask, is this further condition enough? Well, here's an example. Let's let T end 7 and C7, tensor C7, tensor C7 be the tensor with T end 7 of A star equal to the following space. So I have to write down a 7 by 7 matrix. And I claim that the border rank of this tensor is greater than 7, but it is end closed and abelian. So I leave it as an exercise to check that this is an abelian subspace and that it is closed under endomorphisms. The more difficult part is to show that the border rank is greater than 7. Notice we had to go to 7 dimensions. I do not know for sure, but I expect that for dimensions less than 7, the condition of being n-closed is sufficient. So I'm going to do a more general setup to prove the claim. And I'm going to take a detour. It's a very nice detour. It's very geometrical. So we'll back to a general situation. Situation T in A tensor B tensor C. These can have any dimensions. This is dimension A, dimension B, dimension C. Completely general situation. So proposition. So given a tensor. Well, this is a kind of review. That the rank of T is at most R if and only if there exists an R plane in the Grassmannian such that E is spanned by R rank 1 elements and that T of A star, oh wait, I want it in B tensor C. T of A star is contained in E. So this is for any border rank, or any rank. And 2, the border rank of T is less than or equal to R, border rank now, if and only if there exists a curve ET in the Grassmannian such that for T greater than 0, E is spanned by R rank 1 elements and T is in the limiting plane. We call that E0 in the Grassmannian. Note that the Grassmannian is compact, so the limit will exist as T goes to 0 as long as the curve is continuous. Or a, yeah, so the proof of this, T of A star, subset. So the proof is an exercise. Just amounts to translating things we've already discussed. But this proposition has an important corollary. Now let's go back to T being concise, and well, let me be safe in this situation. And if it's a minimal border rank, then when I look at this space T of A star, and I intersect it with the Segre variety, the rank 1 matrices, that this intersection is non-empty. So let me give the proof. So proof for t greater than 0, we have that ET intersect the Segre is not equal to the empty set because ET is spanned by points of the Segre. Right? I mean, it's spanned by rank 1 matrices. Well, what can happen in the limit? In the limit, those R points may crash into each other, but they cannot all disappear. So therefore,
Do you mean second variety or second variety of segre?
I mean the Segre. Yes. Because, and I'm going to give the proof. So let's be sure we understand the statement. T is concise of minimal border rank. Then I look at the space spanned by T of A star. That sits inside P of B tensor C. And I'm asserting that this space must intersect the rank 1 matrices. Okay? Well, you see, because now this R plane is now an M plane, so what will happen here is that this T of A star is actually equal to E0 because they both have dimension M. But E0 is the limit of spaces that contain a rank 1 matrix. It's a closed condition for a linear space to contain a rank 1 matrix. So if I have a curve of linear spaces that contain a rank 1 matrix, the limiting point on that curve must also contain a rank 1 matrix. Questions? Well, proof of claim. I claim to exercise this space intersect the Segre is empty. Now, the good news is that you can check this by hand in an example like this. The bad news is this condition is more difficult to write down as a collection of polynomials. Being closed under endomorphism or being abelian, there's nice, easy polynomials. But to do this as polynomials, it's almost like in elimination theory or something. So this is a further necessary condition, and it shows that even all those conditions we wrote down earlier are not enough. Well, Let's go a little bit further with this intersection property. I'll make a stronger statement. So I claim, so let's again let T be 1A generic. So there's an alpha that we want. And the border rank of T equals M. So this will be T in Cm tensor Cm tensor Cm. Then there exists a complete flag say 0 contained in A1, contained in A2, contained in AM, which is A. I guess I want this to be A dual. Dimension of AJ equals J, such that P of T of AJ, and now this is what you wanted before, intersect the jth secant variety of the Segre. It's not intersect, it's contained in. So the first step of this thing was the corollary, that there's at least a line in the image that's contained in the Segre variety. But there's also a two-plane in the image that's contained in the secant variety of the Segre. There's a three-plane in the image in sigma 3 of the Segre in the space of rank 3 matrices. So let's prove this generalization. Proof. Write T of A star as the limit as T goes to 0 of the span of some x1 of T up to some xm of T, where each xj of T is some curve, well, let's say it this way, in the Segre, PB cross PC, because the plane is spanned by m rank 1 matrices for all T not equal to 0. So if we take P of AK to be equal to P, the limit as T goes to 0, the span of x1 of T up to xk of T, well, the span of x1 up to xk, that's the span of k rank 1 matrices. So any matrix in the span here can have rank at most k. So for any T not equal to 0, any matrix in this span has rank at most k. That is, any matrix in this span is contained in the kth secant variety. But that's a closed condition, to be contained in the kth secant variety. So when we take the limit as T goes to 0, the limiting point must be also contained in the kth secant variety. That's a nice proof. I like that. Questions? Well, we don't need to stop there. We can take this even further. I'll just give a sample. Well, let me make this the remark. There exists infinitesimal versions of this result. And I'll just give one example to give you the flavor. Proposition T is above. Then if P T of a dual intersect the seg ray, we know this is non-empty. So the smallest it could be is 1 point. So if our limiting intersection with the seg ray is as small as possible, so this is border rank M, but perhaps very far from being rank M, then I claim that the intersection with the tangent space contains a line. So let me explain. So this tangent space here is the naive tangent space you get by taking tangent vectors to curves. We don't need the sophisticated algebraic geometry tangent space, just the naive, because this is a subvariety of a vector space. So we know what a tangent vector to a curve is in a vector space. We just take the union of all the tangent vectors to all curves passing through Z that lie on the seg ray. We get a nice naive tangent space. And then we take its projective associated projective space. We intersect this tangent space and our linear space, and this must contain a line. Let's do the proof. Am I going too fast still? A little. Oh, maybe a lot.
What do you mean the infinitesimal? What do you mean?
Well, because this is about a tangent space. You get a tangent space. Infinitesimal to me means it involves derivatives. And you get the tangent space by taking one derivative at a point of curves. There are results involving higher derivatives that I will not state today because they get more complicated to state. But this is a very nice thing to state. It just involves tangent vectors. And the tangent space to our variety, we can even draw a picture. We have our variety. I only know how to draw one picture, as you've figured out by now. We have its tangent space at Z0, but of course this is a bad picture because I need higher dimensional. So let me draw a different variety as some kind of surface. So I take the tangent space to our surface at a point, and then we have our given linear space. So this is this tangent space to z of the Segre, and then we have our linear space t of a star, and this intersection here. This is a very bad picture. Do not draw a picture like this. This is terrible. What?
You must pass through Z.
Oh, yeah, okay. Yeah. Anyway, so there's some line of intersection between these two spaces. I should not have done that. Let's erase this bad picture. Right. So again, let's do the same argument over here. Argue as before. We consider the limit as t goes to 0 of x1 of t, x2 of t, the span. So t of a star is the limit as t goes to 0, x1 of t, up to xm of t. And we know that x1 of 0 is equal to x2 of 0, because otherwise there would be two distinct points in the intersection, and we assume the intersection is one point. So this z is equal to this x1 of 0 equals x2 of 0, because those points cannot disappear, they can only collide into each other. Well, but then the limiting plane here, this will be how to say it? Yeah. So let's just, for psychological purposes, let's pretend x1 is stationary. Then when we take the limit here of this two-plane we have, well, I could draw that. This picture I could draw actually, because this is my favorite picture. So we have x1 of t and x2 of t, and we have the line they span. And then we have here z, which is x1 of 0, which is x2 of 0. So it's the same picture as before. These secant lines must limit to a tangent line on z. So, C picture. This limit is contained in the tangent space to z of the Segre. Okay.
If you are confused, it's a little bit more complicated.
Sorry?
If anyone is confused, you should notice it, right? Because it's a little bit more complicated. Just a tiny bit.
I don't know if I understood that comment, but let me just finish with, I'm going to end a little early so we have a short break before Yarek's talk. But one more remark. So now we've seen there are all these conditions, And these conditions are very difficult to express as polynomials, but they exist. And so one hope let's say we might hope that if Strassen's equations are satisfied, under favorable conditions, you might hope that if Strassen's equations are satisfied, i.e. that T of A star T alpha inverse in NB is abelian, maybe plus other conditions discussed, maybe the tensor does not have border rank M, but that at least that the border rank of T might be close to M. I mean, we've seen it's kind of maybe too much to hope for equality. And this picture, when M is large, you don't see this phenomena for small values of M. But when M is, say, 8 or greater, consider the following picture when T of A star looks like this. So we have some stuff along the diagonal. And then we have stuff in a corner. And 0 elsewhere. Well, this is clearly abelian. So this is, say, less than M over 2. And this is less than M over 2. This is clearly abelian, and in fact enclosed, because in fact the product of, well, if I have some generic subspace here that is abelian and enclosed, because the product of any two such matrices, if I forget about the diagonal, is 0. Right? But you see, this T I could really write as some T1 plus T2, where this is some A1 times B1 tensors C1 plus AM tensor, BM tensor CM. And this thing sits inside Cm minus 1 tensor C M over 2 tensor C M over 2. And this could be generic. And I would still get all the properties we discussed. So in particular, the border rank of T could be around 3/8 M squared, because that's the maximum thing here. Or rather, sorry, M squared over 8, if I did that right. Versus M squared over 3, the maximum. So we could basically have very close to maximal rank just by having our tensor be what we want and then some stuff in the corner. And so next time, I'll discuss this situation. Well, maybe not next time. I will discuss this situation later. So I'll stop here for this afternoon.